After complete discussion of the molecular motions in 3 dimensions, now I like to show the features what happens when the molecules are moving in one direction. Let us consider the molecules are moving along this x-axis. Moving along this x-axis. This is origin with the range of minus infinity to plus infinity and with the velocity, and velocity is u, and the range of u is full range minus infinity to plus infinity with this origin at this middle. Now, what will be the form of Maxwell distribution of molecules in one-dimensional motion? And this one dimension have been taken along this x-axis with this velocity u. So the probability of a molecule to have the velocity u to u plus du is this small range along this x-axis, can be given as the probability we can write this Pu, probability of a molecule to have the x component velocity u within the small range du. This is equal to Fu and du. We have already considered this. The probability will have some function, and this is called the x component velocity distribution function, and du is the range, and this Pu equal to dnu by n, and it can be said the probability of a molecule to have the x component velocity u within the range du, or you can say fraction of the molecules are having the x component velocity u within the range du. So, and this Fu is called x component velocity distribution function. And this function is exponential in nature, and this function may contain u square but not u. We have discussed earlier, due to the isotropic motion, isotropic nature of this motion, since the probability of a molecule to have the velocity 0 to plus infinity will be the same with this probability moving from 0 to minus infinity, and means the molecules will move in both the directions with equal probability. And to maintain this equal probability, this function must not contain u but may contain u square. And already we have defined this one is a and e to the power minus b u square. A and b, these two are constants. depends on this nature of the gas and the temperature. This A and B, in this case also we can calculate, we can evaluate from the normalization condition of this distribution function. And this normalization condition is that minus infinity to plus infinity, and Fu and du must be equal to 1. Means all the molecules are having the velocity minus infinity to plus infinity, the fraction will be equal to 1, or probability of a molecule to move minus infinity to plus infinity must be equal to 1. So if we integrate and equate with this A, then we can get this value in terms of B. Say this A will coming out, A is constant, minus infinity to plus infinity, and instead of this one we can write e to the power minus b u square and du. And this value we can write a 2a 0 to infinity, as here u to the power 0 and power whenever the even, it could be written as in this fashion. If the power becomes odd, then this whole value of this whole integral will be equal to 0. So this one and e to the power minus b u square and du, and this integration would be evaluated by the use of this gamma function. So this is equal to twice a and into half, and gamma, you know, I can also remind you that this gamma 0 to infinity x to the power a e to the power minus b x square into dx equal to half gamma n plus 1 by 2 and divided by b to the power n plus 1 by 2, yeah, 2 you can write. So this is the formula. So here in this case n equal to 0, so it will be half and divided by b to the power half, and gamma half you know is equal to root over of pi. So this 2 cancels, so it is a and root over of pi by b. So this integration is, or you can write integration is a into root over of pi by b equal to 1. So a equal to root over of b by pi. So actually we can get this value of a equal to root over of b by pi. Now the value of a b you can calculate by borrowing data from kinetic theory of gas. And you know the in kinetic theory of gas, this epsilon x bar means x component kinetic energy, average x component kinetic energy of a molecule is equal to half k, and this is obtained from this kinetic theory of gas. And also this epsilon x bar is equal to half mu square bar. M is the molecular mass and u square bar, it is the mean square x component velocity. Here, since all molecules are moving in a particular direction along this x-axis, so in this case the molecules motion of the molecules have a particular direction and also magnitude. So I think it is better to call velocity instead of speed. Whenever it is moving in a particular direction, we call the velocity, not speed. So if we equate these two, then half m u square equal to half kt, or half cancels. So u square bar equal to kt by m. However, this u square bar, u square bar can be evaluated from the distribution of molecules in one-dimensional motions. Say u square bar, every distribution would be utilized to find the average value of a particular property. If we know the distribution of that property, then u square bar is equal to integration minus infinity to plus infinity and u square and fu and du. So if you put here fu, then this will be a is coming out and minus infinity to plus infinity and u square, and instead of fu, a into e to the power minus b u square and du, and this is equal to, and here also you can see the power of u is an even function. 0 is also even function, even number. 2 is also even number. Whenever it becomes even number, it could be written as twice a, 0 to infinity, instead of minus infinity to plus infinity, we can divide it 0 to infinity and u square e to the power minus b u square and du, and this one equal to twice a, and here if we utilize this gamma function format, then here a equal to 2. So this will be equal to half into gamma 3 by 2 and divided by b to the power 3 by 2. So 2 and 2 cancels and gamma 3 by 2, so a into gamma 3 by 2 equal to half and gamma half divided by b to the power 3 by 2, and this is equal to a by and this is pi. So A into half into root over of pi divided by B cube. So this is the U square bar mean square x component velocity and its value from the kinetic theory of gas we have already deduced kT by A. So if we equate then kT by m equal to A by 2 into root over of pi by B cube. It is 3 by 2 then if we put the value of A is equal to root over of pi by B into root over of pi by B cube. B by pi into root over pi cancels and b square and root over of 1 by b square. So it is also 1 by 2. A value this one, half and this one. So this is equal to 1 by twice b. 1 by twice b. So B equal to m by 2 kT. So here B equal to m by 2 kT. So value of A and B have been calculated by the use of the normalization condition of this function and by using the data from kinetic theory of gas. So this A equal to, putting the value of B here, root over of, or you can write this m by twice pi kT to the power half. So the distribution law. So the distribution law in one component molecular motions, this dnu by n equal to A into e to the power minus b u squared into du. Or if we put the value of A and B here, then it is m by 2 pi kT to the power half e to the power minus m u squared by twice kT and du. And this is equal to, you can write this Fu into d. And this x component velocity distribution function, this Fu will be equal to this A into e to the power minus mu square by twice kt, or you can write m by twice pi kt to the power half to the power minus mu square by twice kt. Okay. So if we plot and from this distribution function, we shall also calculate the average value of this x component velocity. Average value of x component velocity means u bar, average value, and this will be equal to minus infinity to plus infinity, and f and u and f u and du. This is equal to, this a will come in outside, and minus infinity to plus infinity, and instead of fu, a e to the power u into the power minus b u square into du. So it is the power of u is odd function, and whenever power of u is odd digit, odd value, then the total value of this integration will be equal to 0. Total value of integration will be equal to 0. This is very interesting to interpret physically. Means all the molecules, half of the molecules are moving from 0 to plus infinity, and half of the molecules are moving 0 to minus infinity. So the average value is equal to 0. If the average x component velocity would be other than 0, then there will be probability for the molecules to move in a particular directions with more likely. Means suppose the molecules having the more probability to move 0 to plus infinity than 0 to minus infinity, then there will be a mass flow of the molecules along this 0 to plus infinity directions, and that will destroy the uniformity of this molecular distribution in this vessel. Uniform distribution will be destroyed, will be hampered. So this x component, average value of x component velocity must be 0, should not be other than 0 value. If we draw the graph, this fu versus u, then suppose this is the fu. When u equal to 0, then fu equal to a e to the power 0, it will be 0 equal to 1 a. So fu equal to a, and this e to the power minus mu square by twice kt, always less than 1, fraction, always fraction. So this is the maximum value. When the velocity, x component velocity is equal to 0, this is the maximum value of the distribution function. With the increase of u in either direction, means from 0 to plus infinity or 0 to minus infinity, the value of this function will be decreasing exponentially and becomes asymptotic. So this curve will be like that. Here this one. This value is A. This value is A when this u equal to 0. And this value of this function is decreasing exponentially and becomes asymptotic. Here also 0 to minus infinity, the same feature will occur as this function contains u square. U may be positive or u may be negative, but u square will be always positive. So this distribution function will be always positive value. And now we shall see what will be the effect of temperature. What will be the effect of temperature on this distribution function? Again, I can remind you that this value. So u bar equal to 0, our equal. And in this case, whenever this u equal to 0, this curve attains maximum. Means the most probable x component velocity is equal to 0. So this UMP, most probable x component velocity, is also equal to 0. Is also equal to 0. Means whenever u equal to 0, this FU attains this maximum value. Now we like to see very interesting feature, the effect of temperature on this distribution function. And this distribution function Fu equal to m by twice pi kt to the power half to the power minus m u square by twice kt. This is the distribution function. So T is present in these two terms. This is the non-exponential and this is the exponential. At lower t, this will be the higher value. And in this case, whenever t is low, this value is high, means this value is also low. This value is low and this value is high. So when u equal to 0, this Fu equal to A, but this value of A is greater with the lowering of temperature. So this so if we draw here also another curve, this is 0 plus infinity and minus infinity, and here it is Fu. Fu means distribution function. Then at lower temperature, this A will be very this value and this is the A. So A will be greater. At lower temperature, this value is higher. But this is suppose the temperature is T1. T1 is the lower temperature. If we draw this curve at high temperature, when this T is high, at high T, the A is lower. T at high temperature, A is lower. This is the value of A. A is lower. So the peak of this curve is lower at high temperature than at lower temperature. peak of this curve is lower at high temperature than at lower temperature. So this curve suppose here, and in this case when T, and this effect of this term, you can see how this value is decreasing exponentially at high temperature. This e to the power minus mu square by twice kT at high temperature, this at high T, this value, temperature is high, so this value is coming greater, and with the increasing of this u, this curve decreasing. So here is the two terms. This term is trying to decrease, and this term trying to increase. So this, in this case at high temperature, this fall of this curve becomes very gentle. Means it will be decreasing slowly. It will be decreasing slowly means with the high temperature, the peak of this curve is lower, but it is decreasing slowly. The curve is broadened, and the velocity curve becomes more uniform with the rising temperature. And means this at high temperature, this curve is uniform, broadened, with this peak lower. So this one is at the temperature T2, and T2 is greater than T1. So this is the features of this x component velocities distribution curve. Now I like to come to a very interesting feature. Whenever all the molecules moving in one direction, means 0 to plus infinity, and no molecule will move 0 to minus infinity, then what will be happening? What will be happened about the distribution curve and the average value of this x component velocity in 0 to plus infinity directions. So in this case it is AQ du. If we do the normalization, if we put this normalization conditions of this distribution function, whenever the molecules will be moving 0 to plus infinity, then 0 to plus infinity, and this Fu and du equal to 1. And putting this value of fu for a is coming out 0 to infinity, and here e to the power minus b u square into d. As fu equal to a into e to the power minus b u square. So, and this is equal to 1, or a into, if we integrate using this gamma function, a equal to 0, then it will be gamma half, and here half b to the power half equal to 1, or a by 2 and root over of pi by b equal to 1, or a equal to twice into b by pi. Means distribution curve, this value of a is twice of this root over b by pi whenever the molecules are, all the molecules are moving with the limit 0 to plus infinity. So, this distribution curve in one dimension, the distribution curve in one dimension will be equal to twice a to the power minus b u square and d. Formerly it was a to the power minus b u square du. Here 2 is multiplied. Since all the molecules in earlier cases, half molecules are moving from 0 to plus infinity, half of the molecules are moving 0 to minus infinity. Now in this case, all the molecules are moving 0 to plus infinity. So this value, fraction or probability, fraction of the molecules or probability of a molecule becomes twice the value when it is moving minus infinity to plus infinity. Now this here also a equal to m by 2 pi kt to the power half, and b equal to m by twice kt. These values are given itself. These values depend on the nature of this gas, means molecular mass and the temperature. And so, if we calculate this average value of x component velocity with the range 0 to infinity, then it will be 0 to infinity and u and fu d, and this is equal to, if we put this value of du fu, then twice a and 0 to infinity, and here u to the power minus b u square and d, and this one equal to twice a, and this also we can solve by the use of this gamma function. Here n equal to 1. So this is equal to gamma 1 divided by 2 and b. So putting this value of a, putting the value of a 2 into root over of b by pi and into 1 by twice b, and this is equal to 2 cancels and 1 by root over pi b, root over 1 by pi by b. Putting the value So this U bar with range 0 to plus infinity equal to, putting the value of B, it will be root over of 2 kT by pi L, or you can write this 2 RT by pi L. So formally we have seen this U bar equal to 0, U bar MP equal to 0, and U square bar root over equal to root over of KT by A. This could be obtained from this average kinetic energy of average x component kinetic energy of the molecules. So this is root over KT by M. Here, whenever it is moving in one dimension, in a particular direction 0 to plus infinity, so it becomes like this. And you can say why this value is so important. Now, I make an arrangement. Suppose here is a globe. Why this x component velocity 0 to plus infinity becomes so important in practical sense of this term? So here it is, say globe, and here there is a small hole, and here the cesium, one metal, alkali metal, cesium have been kept within this globe, and it is heated up. It is heated up to a temperature, suppose 500 degree centigrade. This globe have been kept at a temperature of 500 degree centigrade. So the cesium metal, solid metal, becomes vaporized and will be cesium atoms. And cesium atoms will move in all directions with equal probability. But whenever it is striking this wall of this globe, it is rebounding. It rebounds. But whenever it is moving, it is just striking this hole. It is escaping. It is escaping from this hole. And several cesium atoms will escape from this hole and will form the atomic beam. This is cesium atomic beam. So if we like to produce the atomic beam of a metal, then we shall have to take this arrangement. And here all the cesium atoms moving from 0 to plus infinity. 0 to minus infinity, they are not able to move. They will be rebounding from this wall of this globe. So this, if we consider this U bar with U bar of the atomic beam of cesium atomic beam, then it will be equal to root over of twice RT by pi M. M, the molecular atomic mass of this cesium, T, the temperature, R, the universal gas constant. So if you put here this root over 2 into R equal to 8.31 joule mole inverse secondary inverse, and temperature is 273 plus 500 Kelvin. 500 Kelvin and divided by pi equal to 3.14 into atomic mass. Atomic mass of this cesium is 133 and it is kg mole inverse. 133 kg mole inverse. So mole inverse cancels, Kelvin inverse Kelvin cancels, and joule by kg, root over joule by kg, it will give you meter per second. We have seen in earlier problems, and this value will be equal to 175.5 meter per second. So the average velocity of this cesium atomic beam at 500 degrees centigrade becomes 175.5 meter per second. So this is very important in practical cases where we like to see what will be the average velocity of this metal atomic beam. Now as usual, I like to convert this x component velocity distribution in terms of the kinetic energy distribution when all the molecules are moving along this x directions. So here this dnu by a equal to m by twice pi kt to the power half e to the power minus mc square, mu square by twice kt into du. So the average kinetic energy epsilon bar equal to half average kinetic energy equal to half u square. Average kinetic energy in along this x component. It is half m u square. U the x component velocity with the range minus infinity to plus infinity. So u square equal to twice epsilon x divided by m, twice epsilon by m, or u equal to root over 2 by m and epsilon x to the power half. So du, we shall have to replace this du and u square. U square equal to this value, or half m u square equal to epsilon x. It is not very much problem to substitute. And in this case, du u equal to this one. So du equal to root over of twice m into half into epsilon x to the power minus half into d epsilon x. Or you can write it to here 1 by root over of 2 and this m 2 to root over 2 will be coming up and it is epsilon x into d epsilon x. So the kinetic energy distribution of molecules along 1D motion, one-dimensional motion, it becomes the n epsilon x by n. It is the fraction of the molecules having the x component kinetic energy epsilon x to epsilon plus d epsilon x to d epsilon x to epsilon x plus d epsilon x. And this will be equal to here m by twice pi kt to the power half, and here e to the power minus epsilon x by twice kt from this value half m u square equal to epsilon x by 2 kt, and instead of du we can put here 1 by root over of twice m epsilon x and d epsilon x. You see here m and m cancels, and root over 2 and root over 2 it becomes half, and 1 by pi kt to the power half kt to the power half into e to the power minus epsilon x by twice kt into 2 already been cancelled, and here epsilon x to the power minus half and d epsilon x. So this is the kinetic energy distribution. So kinetic energy distribution we can write here. We can write one by 2 and 1 by pi kt to the power half to the power minus epsilon x divided by twice kt into epsilon x to the power half minus half and d epsilon x, or you can write 1 by root over of epsilon x into d epsilon. As usual, you can see in kinetic energy distribution in kinetic energy distribution, one very important feature is that the distribution is not dependent on molecular mass. Only it depends on the temperature. So the kinetic energy distribution also, as before, does not depend on the nature of this gas. It depends only on temperature. At a given temperature, all the molecules will have, all the gases will have the same kinetic energy distribution. It only depends on the temperature, not the nature of this gas, as the molecular mass is absent. So from this value, we can also calculate this average value of x. Average value of x we can also calculate. So it is better half m u square bar, and u square bar we have already calculated. So u square bar we have already calculated kT by m. So putting this value is half m into kT by m cancels, so it is half kT. So in a particular direction, average kinetic energy is equal to half kT along this x-axis. Similarly, half kT along this y-axis, half kT along this z-axis. And whenever we shall consider the average value in 3D, average value of this kinetic energy in 3D motion, it will be half kT plus half kT plus half kT equal to 3 by 2 kT. In future, I will give a lecture on this law of equipartition of energy. Any in a particular directions, the kinetic energy, average kinetic energy equal to half kT. We shall see in my next lectures. Now today's lecture is complete, and every possible features of one-dimensional motion of the molecules have been explained, and in my next class I will try to discuss the molecular motions in two dimensions, along this x-axis and along this y-axis. This will also be very important, especially whenever we deal with the chemical kinetics of a reactions. So thank you all who are watching my video. I hope I shall be able to explain, at least to some extent, the matters which may be a benefit of my viewers, of my dear viewers. Thank you all.